Welcome to the University of Utah CS4400 Lab number 10 overview. Today we're going to go over the allocator example. I have downloaded the allocator files, the working list binary, as well as the main.c that has a few problems. Let's start with the list binary and see how this is supposed to work. So if I run list, I can add items just by typing them. I can use question mark to view the list items, and I can remove items just by doing minus to take items out. And everything seems to work just fine. Now, if we do the same thing with our main, so I'm going to go ahead and build our semi-working program. I'll go ahead and run main. And let's add a few items to the list. And that seems to work just fine. If I go ahead and try to remove an item, though, it doesn't seem to work. Well, inside the lab instructions, what it suggests is that we go into the source code and we add ourselves a checking function. So let's just go over this source code first. We have a main method. It simply parses through the input of the user, allowing them to add items, unless they've used a negative, which will remove an item, unless they use the question mark, which will show items. There's a readline function. We won't mess with the readline function. It works just fine. The key to this is in this linked list allocator section. There's going to be a block of memory allocated, and within that block of memory, it will be divided up into structures of 3 pointers. Those 3 pointers, one pointer will be to the data, the second pointer will be to the previous entry, and the third pointer will be to the next entry. So we have a double linked list here. We have 2 pointers here. One's defined as the head, and one is defined as the tail. These will contain pointers to the head and tail of our list. At this point, it starts out as null. We have a variable that has the heap size, which will be 4K. We also have a heap pointer, which points to the start of the heap, and a new allocation pointer. This allocation pointer merely points to the area within my heap where the next instance of my list will be allocated. And this initializer allocates the memory, assigns it to heap, initializes it to 0, and then assigns the beginning of the heap to the next allocation pointer. Those are pretty straightforward. We'll leave those alone. But let's take a look at the addString method. In the addString method, we first parse through the list, starting with the head and working each entry one at a time according to the next pointer, and we compare it against the string that was passed in. If we find a match, whenever you not the stir compare, that means you successfully found a match, it will return. This means that we simply will not add duplicates of the string to our list. But if we can't find it, we assign the next allocation pointer to our L temporary variable, advance our next allocation pointer, check to make sure we haven't exceeded our memory size. We only have 4K. If our next allocator pointer is past that 4K limit, we show out of memory error. We then assign our data to this pointer, set up the structure, and exit. The remove string is a bit simpler. It's looping through each element, comparing to see if it finds a duplicate. If it does find a duplicate, then it adjusts each of the next and previous pointers to the other elements. So to the previous element, it adjusts its next to point to the current element's next. And if there's a next, it adjusts the next previous to the previous, basically removing itself from the list. It doesn't do any deallocation. There's no collapsing of memory, nothing like that. It just simply removes itself from the list. And then the show string, which goes through each element in the list and displays the data element. Well, we saw that this didn't work, and what we're encouraged to do, according to the lab instructions, is to create ourselves a check function. So I'm going to go ahead and create this check function. Now, there are several things that this check function needs to do. The first thing it needs to do is it needs to go through the list and make sure that for each entry in the list that its previous pointer matches the value that came previously. Well, I'm going to initialize previous to null, simply because that's what the head should be referencing. And then I'm going to create myself a for loop. For is going to start with the head. It's going to make sure that that the current element is not null, and then it's going to just simply advance through each element. So what will this particular for loop do? Well, it is going through each element, and it is checking to see if the previous item for my current element is equal to previous. If it's not equal, we're going to go ahead and display an error. And we'll say previous is incorrect. Whether or not it is incorrect, we want to change the previous pointer to what we are currently looking at so that the next comparison will work fine. Once that loop is done, whether it's successful or not, the instructions tell us that we need to test to make sure that the tail is set correctly. And that's very simple. If L has become null, that means previous should be the tail. So if the tail is not equal to previous, then we print our error. And this time we'll say tail is incorrect. All right. With that check function, we'll go down here and add the check function to our add and remove. So just simply check there at the very end, and at remove string, we will check here. It builds successfully. So let's go ahead and run this. So let's see if we can figure out where the problem is. I'm going to go ahead and add 1, 2. Oh, we immediately see a problem. It seems that the previous is always incorrect. Well, why could that be? Well, let's come up here to the add string function. Here's add string. Now, add string doesn't really do much with previous here. In fact, I don't see a single reference to previous inside this particular function, which is a problem. Now, we don't need previous when we're walking through the list, checking to see if we have a duplicate. And we don't need previous when we're just simply finding the next structure element within our allocated heap. But as we're organizing that entry within the list, we really should update the previous value in the structure. So I'm going to go ahead and add previous for L is equal to. Now the question becomes, what should this be equal to? Well, this is the last element in the list. This is the new last element in the list, so it should point to the tail. That means that the tail, whatever was tail before, is now going to become the previous value of our current element. And our new tail, down here in line 118, will become the current element we're working on. That should resolve our problem with creating elements. So let's write that. Let's build it, and let's run it. So I'm going to go ahead and add 1, 2, 3, 4. Everything seems to work just fine. So let's try to remove some elements. I'm going to go ahead and remove element 2. Oh, I've just now added a duplicate. Oh, hey, it does duplicate checking. Now I'm going to remove 2. It's successful, no problems. I'm going to remove 1. Now we're getting an error message. It's telling us the previous is incorrect now, and it doesn't actually remove that item. This is the error that we saw before. Well, let's go ahead. I'm going to quit this. Let's take a look at our removal function. So when we remove a string, we are looping through one element at a time, checking to see if the data pointer for that element matches. If it does, we check to see if the previous pointer is null. If it is not null, then we take then we go to that previous value and we assign to the next pointer of that previous element the next value that was contained within ours, whatever that may be. But the question becomes, what if previous is null? That is the case whenever we're working with the head element. If the head element is being used, the head element's previous value is null. Well, the problem here is we need to handle that particular case. But what should it be? Well, if the head element is no longer going to be this current element, clearly we need to assign head something else. Probably the next element. This should take us out of the list. Let's go ahead and write this and see if it works. Make it, run it. So I'm going to add a few elements, make sure it's correct, and let's take out 1 and see what we got. This looks great. We should be able to remove a middle element. That looks good. And we should be able to remove the end element. Oh, now it's telling us our tail is incorrect. It did remove it successfully, but the tail value is not correct. And anytime we go ahead and try to add a new item, this doesn't work. So why is that? Well, pretty much for the same reason that removing the head element failed. If we're removing the tail element's next value is null. But we're not updating the tail pointer here. We're just simply updating if there is a next item. So let's go ahead and update tail. And tail is just simply going to be our previous, the current element's previous pointer. We'll write that. We'll build it, and let's give it a go. 1, 2, 3, 4. Make sure it looks good. Remove 1, success. Remove 3, success. Remove 4, success. Add 5, and we have 2 and 5. This program seems to be running just fine at this point. So let's add a bunch of elements. 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22. And we've run out of memory. Well, this is odd because we're getting a block of 4K and each element should only take up 24 bytes. Now, if we take a look using the handy-dandy internal calculator of Bash, If we take a look, we should be getting 170 elements, but we're not. There's not 170 values added to this list before we ran out of memory. Well, it's something to do with the add. Obviously, remove string didn't cause us any problems. We weren't removing anything. But let's take a look at add string. Now, add string, whenever it's checking to see if we're out of memory, is actually checking to see if the new allocating pointer just exceeded heap plus heap size. Now, heap plus heap size there's nothing unusual about that. The problem is with this the alloc underscore p. When the alloc underscore p is adjusted, we're advancing the current pointer by a certain amount. In this case, we're advancing it by link pointers times size of void pointer. Well, size of void pointer is 8. That's the size of a particular pointer value. And link pointers is 3, as we saw before. So this gives us 24. So we're adding 24 to L. What is L? Well, this is where things are broken for us. L is a void pointer pointer. Now, whenever you're advancing a void pointer, it doesn't understand what the data type is. A void pointer data type is undefined. The C advances it per byte. But a void pointer pointer is a defined data type. It is an address or pointer to an unknown data type. Well, pointers are 8 bytes. And so what we're doing here when we advance our void pointer by 24, we're advancing it by 24 pointer values. This is not what we want. There's really 2 ways to fix this. We can either change this so that it doesn't advance 24 void pointers. We could actually take out the multiplication to size of void and it would fix the problem. But maybe the simpler method is just simply to take out that extra pointer. So now L is just a void pointer. Is this going to break our program? Not really. Since we're only really accessing L to get our data through the macros, and if we take a look at the macros, we can see that every one of these macros already casts L to a void pointer. So everything's taken care of there. We don't have to worry about the data type that's being used by the add. We'll just simply make it a void pointer. So let's write this. Let's build this. And let's run it. We'll use letters this time. And I've added 26 letters, not necessarily in a good order, and it seems to all be there. Question is, can we add all 170 items? Well, I'm not going to type them in individually, but I will do this. I'm going to for I in, we'll go ahead and give it my number range. We're going to use the printf of $I, and then pass this all into my main program. What am I going to put in the printf? Well, I'm going to pretend like it's actually me typing. I'm going to do a %D here with a carriage return. And then I'm also going to have it print out the list. So it's doing 2 things. It's inserting the number, and then it's printing out the list. We run it, and as you can see, it gets to number 170, and before it can add number 171, it shows out of memory, just like what we expect.